Huh? Do you see this table? Hello?
Yes.
Yeah, sure. Yes.
Why are you taking a lot of time to respond? Anybody has a right to respond. You don't wait for somebody to respond on your behalf. So, when we are, these are the things that we are going to look on. We have a negation. This is a symbol for that one. And the one thing.
Your audio is breaking. Your audio is breaking.
Disjunction, this is a symbol, and it means or. Conjunction is denoted by this symbol. Sometimes
We can see your screen.
Mwalimu, your audio is patchy. You cannot hear you.
Audio net yako ni mbaya.
Secondly, we can see your screen.
Hello.
Yes, we can see your screen.
Can you kindly work on your network?
Make sure you don't speak in a hurry unless you have something to big. Do you hear me now?
Yeah, sure, but your screen isn't being shared.
Okay, let me share. I can see somebody, Gabriel. You have raised your hand. Gabriel, do you have something? Now you can see my screen again.
Yeah, sure.
Okay. Yes, we were talking about the proposition, and I had shared this table, and I was just explaining what you are going to expect, because this negation, this is a symbol of it, and it means not. Disjunction, this is a symbol of it, and it means or. Conjunction, I said we were here. This is where we have this denoted by this symbol, which is a kind of a, and it means and. Some cases you may find that this symbol can be the opposite of this without need this line, which is making it a. So when you get it, you will just understand it means conjunction or it means and.
The screen is not visible.
Hatuoni symbols ba.
Yes, somebody is raising an hand.
Mwalimu, you cannot see your screen, bwana.
Is it Frank?
Oh, God.
Okay.
We can see your screen, but we can't see the table. The document that you're trying to read from isn't open on our side.
So, and then conditional, it means it is allow, and it means it, if, and then. By condition, it is this sign, and if, and only if. This is what it means. Are we there?
Mwalimu, you are teaching us the files, but
not seeing anything.
you are teaching us the files.
Yeah, we are viewing File
It's a
Explorer.
video lag.
Pardon?
You're experiencing a video lag.
You are teaching us the files.
The files. What do you mean by files?
You are
Your
under
screen is-
document.
Eh?
Your screen
There's a
is
You are
video
showing
lag
us
from our side.
Can somebody speak? Maybe I hear. There is something which I'm not getting. I had shared the yes. Who is that one? Arisia. Yes.
you are showing
I've
us the
stopped
documents
sharing the
instead of the
screen.
file.
I have stopped sharing the screen so that I can hear. Maybe Ombaka. Ombaka, you were saying
You are
something.
showing the documents.
Yeah?
Like you are under the document, under files. You are not showing us the file that you are talking about.
I am under the file.
Yeah.
Okay, did I the screen? What do you see in the screen?
File Explorer.
Documents,
Eh?
discrete mathematics, discrete
File
mathematics
Explorer files.
documents are
Oh,
not.
I shared the folder, the folders.
Yes.
Yeah.
Oh, sorry for that. Let me sharing. Now you can see.
Yeah, sure. Wait, it's loading. Yeah, sure.
Yes.
Yes, we can.
Perfect.
Oh,
Perfect.
it's okay now. Oh, it's okay. Thanks for that correction. So I was here in this table. This is where we were. Then I was explaining this one. Somebody is using Google. We can hear the echo. Can you mute? Who is that?
Franklin.
Mute, please. So I was explaining this is a conjunction where we have this is a sign and it means end. And I said that this one can be the opposite of this one, but now without this line, which is making A. So, and then we have conditional. Conditional, this is the sign, and it means if and then. By conditional, it is this sided arrows, which means if and only if. Are we there up to that point?
Yes.
Are we there?
Yes.
Okay.
Yes.
Now let us proceed, and this is what we are going to get. And this we are starting from negation. The negation of a statement is generally formed by writing the word not, like you saw it from the table, at the proper place in the statement, or by prefixing the statement with a place, and it is not the case. It means it is not the case. If P denotes a statement, then the negation of P is written as B, and the readers not P. If the true value of P is true, then the true value of P is false. So, in other words, if you are being told that P is not P, then you are being given P to be true, then also you know that that's P is false. Also, if the true value of P is a false, then the truth value of P is true. Like now you can see here, P is not P. This is true. This one's false. This false, it turns to be true. Is what we have explained here. So, for example, Consider the statement P. Kolkata is a city, then it is not true. There is then the again of this P, Kolkata is not a city. Although the two statements, Kolkata is not a city, it is not the case that Kolkata is the city, or not identical. In this case, we have translated both of them by P. The reason is being that they are of the same meanings. So in this case, so once it is being given that this B is not P and it is turns to be true, like now we were focusing on this statement that we add here. Kolkata is a country, and then somebody is talking here that it is a city. So that statement, you talk it to know whether it has a value of being true or false. Are we together? Yes, are we
Yeah.
together?
Yes.
Okay. Then another point, another statement we had is a conjunction. And we said, what did we say conjunction is? It did not what? It means mesahau.
And
What did we say? Conjunction is and. So this is the reason why I've given you this table so that you can know what this biconditional means, conditional means, conjunction, and all that. They need to be in your fingertips because these are some of the things we are going to use. So the conjunction of two statements, B and Q, is the statement B and Q, which is read as B and Q. The statement B and Q has truth value whenever both B and Q have the true value of T, which is true. Otherwise, it has a true value of false. So P and Q, this is true and this is true. So it means if P is equals true and T is equals true, then everything is true. So, and if P is true and this one is false, that means everything is false. B and true is false. The same thing applies if P is false and Q is true, then the answers of B and Q are false. The same things apply if both of them they are false, thus means they are false. Consider the following statement: P, it rains today. It is raining today. Q, there are 10 chairs in the room. Then P and Q, it is raining today and there are 10 chairs in the room. Usually our everyday language, the conjunction and is used between two statements which have some kinds of relationship. The statement, when we are talking about it is raining, that's it is raining today. That's 1 plus 1 is equals to 2. It sounds odd, but the logic, it is a perfectly accepted statement from the statement. Because we have adapted it from, it is raining today. So this, it gives the true. When you are talking about and, it means like now it's an addition. Example, translate the following statement: Jack and Jill went up the hill, into a symbolic form using conjunction. So the solution, let B, Jack went up the hill, Q, chill went up the hill. Then the given statement can be written in a symbolic form of B and Q. That's all about conjunction. And then we are now talking of the disjunction. What do we mean by disjunction? What did we say? Disjunction means or, isn't it? Are we there?
Yes.
Yes, yes.
Yes.
So the disjunction of two statements, B and Q, is a statement of P or Q, which is read as B or Q. The statement P or Q has the true value of F, which is false, only when both P and the Q have the truth value of the false. Otherwise, it is true value of T. So that means if you look on this table, we have P and Q. If this is true and this is true, because we are being told that this and this or this has to be true. So if this is true and this is true, so that means the P or Q, there is a truth of it. And what if this one is true and the other is false? That means already we have answered P or Q, one has to be true. And what if these are false and this is true? It is still, we have satisfied this rule. And then what of this portal false? That means everything is false. Are we there?
Yes.
Yes.
Yeah.
Yes.
Yes.
Consider the following statement. P, I shall go to get the game. Q, I shall watch the game on the television. So one thing you are being asked to go, you are saying that you are going to watch live in the game, and another one you watch in the television. Then P or Q, I shall go to the game or watch the game on television. So that means you have two options. You can either choose one and leave one. Conditional propositions. If P and Q are any two statements, then the statement P to Q, which is read as if P, then Q, is called the conditional statement. So that's all what we talked about. This all we talked of conditional statement, and this is what it means. So conditional statement, or they can imply the implication and the connective is the conditional connective. So let us now look on this step. The conditional defined as the following: truth, depot of the condition. So all these tables we have seen, this is a truth table. B, Q. Truth, it turns this one. Truth false, turns false. Truth false. False truth, turns truth. False, turns truth. I don't know whether you are understanding the difference between the first one, which is not, the second, which is and the third one, which is or, and now where we are. Are you getting these points?
Yes.
Yes. So this statement, it gives that this to this, it has to be same. This like now, if this true and this true, then everything is true. If this is true and this is false, then it's false. If this is false and this is true, so we are considering the second option. In this condition statement, Q is called the hypothesis or a prime premise or antecedent, and the Q is called a consequence or a conclusion. So P is an hypothesis and the Q is the conclusion that is made. That's why it is being considered. To understand further, this connective can be looked as a condition of promise. If the promise is violated or broken, the condition or implication is false. Otherwise, it is true. For this reason, the only circumstances under which the condition of P can give a true answer to Q is false is when P is true and the Q is false. When P is true, and the Q is false, then it turns to false. Let us look on the example 6. Translation of the following statement. The crop will be destroyed if there is a flood. Into symbolic form using conditional connective. So you change that one into symbolic, then solution. Let's see, the crop will be destroyed. And if there is a flood, let us write the given statement as if there is a flood, then the crop will be destroyed. So the symbolic form of the given statement is this one. That's how you just write in symbol terms. This statement, you write once you have denoted the given if the values of it, then you give this one. The crops will be destroyed and there is a flood. So this is F to C. So, and let us now look another example. Have you seen this example clearly? Is it sticking to your mind?
Yes.
Yeah? No. I keep on confirming so that I can to confirm whether we are together. If there is maybe a disturbances of the network, I realize that maybe there is a drop out and drop down. I might be talking alone. Have we seen this example?
Yes.
Okay. Let us now move to the next example. Let P and Q denote a statement. You drive over 70 kg per hour. Q symbolic form. So this one, how can you do this? The result is obvious. It's like now what we have done here. You can just do. But now let us do this. Write the following statement in the symbolic form. You will get a speeding ticket from this symbol. Now we are proceeding to see. You will get a speeding ticket if you drive over 70 kg per hour. So this is the condition that you will get at this speed if and only if you drive this. Driving over 70 kg per hour is sufficient for you to get a speed ticket. That's statement. It means like that. Somebody has raised an hand, or yes, there are those synonyms which are appearing in your screen. If you are not careful, you can touch something which can raise your hand without your notice. That's why I'm seeing some people have raised their hand. Unless you have something, you can ask. So, if you do not drive over 70 kg per hour, then you will not get this the speeding ticket. That means this one, it is talking of the opposite or the negative of it, and the same thing is this one, and it gives the question. That's a false and false. So whenever you get a speeding, this is when you are talking. If you do not drive over 70 kg, then you will not get the speeding ticket. So whenever you get speeding ticket, So it's P to Q. And P to Q, that's the first statement is P to Q. You will get a speeding ticket if you drive over 70 kg. So this is P to Q. And this B to Q is the second statement, and this the third statement, which is to say that if you do not drive over 70 kg per hour, then you will not get a speeding ticket. It's this one and this one, respectively. Are we there?
Yeah.
Yes. A point to take a note. In ordinary language, it is customary to assume some kind of relationship between the antecedent and the consequence in using the condition. But in logic, you need to mute when you are not speaking. The antecedent and the consequence in a condition statement are not required to refer to the same subject matter. For example, somebody is not muted. For example, if you pick a statement of if I get sufficient money, then I shall purchase high-speed computer. Sounds reasonable. So, on the other hand, a statement such as if I purchase the computer, then this sense in our conventional language. But according to the definition of the condition, this proposition are perfectly acceptable and has a true value, which depends on the truth value of the component. Depending on what kind of statement you are giving, then it can turn to be true or false, depending. But now, what we are explaining is different from the English terms. You can come up with a statement which is contradicting to the ones that you are searching on, as well as this discrete mathematics is concerned. Some of the alternative technologies used to express B to Q, if P then Q, are the following. P implies Q. That's one of the statement. And another one, if P only if Q. P only if Q. So P only if Q. If P, then Q formulation emphasize the interstate, where P only if Q formulations emphasize the consequent. The difference is only statistic. So B if Q or Q when P. So that's what we all mean here. We may say also Q follows from P, or Q whenever we have P. Another statement is P is sufficient for Q, or sufficient condition for Q is P. The next point is Q is necessary for P, or a necessary condition for P is Q. The last point is Q is consequent of P. So that's all. And then we just look on the converse, inverse, and the contrapositive. If P, only if Q is a conditional statement, Q only then P is called, it is converse. Are we there? Eh? Are we there?
Yes.
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 So, like now, this is the negation of P only if the negation of Q is called it is inverse. The negation of Q only to the negation of P is called it is contrapositive. So you need to mark all this. So the truth table of Q only to P converse of B and Q is what we have. B, if P is true and the Q is true, then Q only to P is true. And if T is true, P is true and the Q is false, then it does the true using this condition. If P is false and the Q is true, then everything is because in the statement we have P only do Q. So this is in the other sense, we value more P than Q. That's why it is if it is true, then this one is false, and then the result is true. If this is false and this is true, then the whole cells it turns to false. And if it is false and this false, then it is true. Because this is the determinant. Truth table for the now what we call the inverse. The negation of P, the negation of Q, the inverse of this one. So this and this one, if this still it is I mean, if this is true and this is true, then this is false and this is false, then it gives the true because this one is true and this is true. So the inverse of it, the inverse of this and this inverse of this is this and this. And if they are that collective, you have that one. What up? And this, if P is true and the Q is false, then the inverse of this one is this, and the inverse of this one, the inverse of this one is this one, then you get the truth. So this, you can check all that one, how it moves to that one. I think you have seen. And this one, when you are coming to the contrapositive, and here we have negation Q to negation P, then you counter check the controversion. The truth of P, if it is true and the Q is true, then the negation of it is false and this is false, and it gives true. So you cannot check that one and all that one continuously until the end. I think we have seen up to that level. Are we moving together?
Sure.
Okay.
Yes.
Let us look on the example. Consider the statement P, it rains. Q, the crop will grow. So, for the crops to grow, it depends on the rain. The implication of P to Q states that. So, the R, if it rains, then the crops will grow. The converse of the implication P to Q, namely Q to P, states that if the crop if the crop will grow, then there has been rain. For the crop to grow, then there has to be the rain. So the inverse of the implication P to Q, namely the negation of P and the negation of Q states that if it does not rain, then the crop will not grow. That is very true because the condition of implication B Q, the negation of Q and the negation of P states that true, if the crops do not grow, then there has been no rain. Yeah, because if the crop did not grow, that means there was no rain. Let us now look on this example. So, construct the truth table of B, P, Q, condition Q, and then Q, condition B. So, B to Q, this is true and this is true. That means that this is true and this is true. Also, the connection of it is true. This is the and. So this is now this and this one that's to be true. And if P is true and Y Q is false, that means P condition to Q is false. But the Q to condition to P, it is true. Because this one determined. So this and this one, it turns to be false. Because the condition was not satisfied. And what of if the P is false and the Q is true? That means the first condition, B condition Q is true, and the Q condition P, that's a false. And the entire turns to be false. Are we together? There is somebody who is not muted. Are we together up to that level?
Yes.
Yes.
Yeah.
Now, once you have seen the condition, now we move to what? This one, the by condition, which means if and only if. So that's where we are. We are now. By condition proposition. If P and Q are N2 statements, then the statement of P only if Q, which is read as P if and only if Q, and abbreviated as P only if and if. This is how it is being abbreviated. Somebody is not muted. Who is that? I think this person needs to be. Who is that? Vincent, are you the one? Kevin. Kevin, you need to. Okay, let us proceed. Are you able to see the screen? Huh?
Yes.
Okay. So in this by condition, this one's like now it is the abbreviated. This one is called a by conditional statement, and the connective is a by conditional connective. The truth table of P if and only if Q is given by the following table. So that means if this can be true if and only if Q can be true. That's what it means. So this like now this the P is true and the Q is true, that means it's true. Q is B is true and this is false, the result is false. If this is false and this is true, then the end result is false. B is false and this is false, that means it has given a true because all are the same. So it may be noted that P and PQ is true only when both P and Q are true, or when both P and Q are false. I get it. So it can, both of them can be true if and only if both of them are true or are false. That's the condition, what it means. So observe that P and Q is the true when both the conditionals P to Q and Q to P are true, i.e., the true value of bit Q, this P condition Q and Q condition P is given on the above exercise that we normally saw. It indicated the true value of P and Q defined there. So this is a repetition of whatever that we saw on the condition, but now it is a progress, which gives if and only if. So I think we have covered all that, those conditions up to that level, and then now we are moving to tautology and the contradiction. Tautology is a statement formula which is true regardless of the truth values of the statement, which replace the variables in it. It is called the universally varied formula or logical truth or tautology. Are we there?
Yeah.
Yes.
Yes. The contradiction is a statement formula which is false regardless of the truth value of the statement, which replaces the value of the variables in it. It decides to be contradiction. And the contingency is a statement formula which is neither a tautology or the contradiction. And this is called contingency. Substitution instance. A formula A is called a substitution instance of another formula P if A can be obtained from P. But by substituting formulas for some variables of P. So you may be having so many variables, then you and these variables of P, you substitute with the condition that the same formula is substituted for the same variables each time it occurs. For example, let us now have an example. Let P, the P condition of J and P, substitute R subconditions S. This is a bicondition. For P in P, we get, so the R is bicondition of to S, which is bicondition to the combination of J and this R bicondition S. Then A is a substitute instant of P. You need to take a note that R subcondition of S is a condition to J and Q. J and P is another substitution instance of P because the variables of P and J, B in J and P was not replaced by this one, by the by condition of this. It was not replaced up here. Let us look on the equivalence of formulas. Two formulas, A and P, are said to equivalent to each other if and only if A by condition P is a tautology. If A by condition P is a tautology, we write A by condition P, which is read as A is equivalent to P. So you mark this signs means equivalent to P. And this is a by condition. And this sign is only a symbol, but not connective. A P is a tautology if and only if truth table of A and P are the same. So if this one, the truth table of A and P, if they are the same, then we can say that this is a tautology, the tautology. The equivalence relations is symmetric and transitive. So method one, truth table methods. One method to determine whether N2 statement formulas are equivalent is to construct their truth table. For example, you need to prove that B all Q is equivalent to negation into negation P and negation Q. Are we there? Are you getting? Hello? Hey.
Yeah, sure.
Hello?
Yeah.
Yes.
Watu wamelala?
No.
Fala.
Okay, when you are not speaking, in my class, when I find my students are not getting what I'm saying, then it means the next time is to think of having a cat to test whether they have understood or not. So make me understand that we are with me so that we can not think of a cat. Because in my class, I like giving my students several cards depending on how they understand. So you need to convince me that you understand in class to avoid any workload. So let us proceed. Are you able to see this table?
Yes.
Okay. So we have said that method one, this for example, this is proof. You need to prove that B or Q is equivalent to negation into negation P and negation Q. So you need to prove that this is equivalent to this. So PQ, we have PQ, we have P or Q, we have negation P, and we have negation Q, and then we have negation Q conjunction to negation Q. And then we have negation into negation Q and negation Q, negation P and negation Q. And here we have P or Q. What is the sign of this one? Means all. Or what is it? Huh?
Disjunction.
Yes, disjunction. And this one?
Equivalent.
Yes. So this is, so in this case, you are comparing this, all of this, like now, this, you need to check whether this one, what is here, is equivalent to what is here, right? Because now if we start from here, just check, because we are checking whether this is supposed to be, we start from here, we come here, what is here is supposed to be what is here, then it satisfies this condition. Then here we have a truth, and here we have a truth. Does that one satisfy? Yes. And then this we have a truth, and this we have a truth. Does it satisfy? Yes. This we have a truth, and then this one we have a truth. Satisfy. These are false, and these are false. It is satisfied. So what about this one? This or this has to be true. So this or this is true, yes. This or this is true, yes. This or this true, yes. This or this, dance variables, of course, they are the same. So this, when you are looking on this one is the inverse of this. So if it was true, this one is not true, it is false. And what about this one is an inverse of this. That's how you check. Don't you see these things are very easy? Are you seeing how they are moving?
Yes.
Yes.
Yes. If you get any kind of question from this, it is not supposed to trigger you in any manner, because these things, when you read them well, even the exam, it becomes like a walkover. This is a poster. This is free marks. If you are given a kind of question, and this one, you need to prove. This one, like now, this you prove if this one is equivalent to this. You do the same, because you have this one and this one. So this you need to, like now when you are coming with it, you understand from your, is it the primary or high school? Which kind of table is this? You understand well. Where you get in statistics. Which kind of table is this? Okay, you can guess and know. So this P condition Q is equivalent to negation P or Q. So you need to come up, we have P and Q. You need to come up with this one, and then you find out the negation of this, and then this. Once you have seen this, and this, like now this or this, that means if you are checking on this one, negation P or Q, that means this negation P is this one, and the Q or Q can be true. So this or this one is true. And what about this one? This one is false, because all of them, they are the same. And this true, that's to true. And this one and this one and this one, this the P, the P and this one, this and this one of them is true. So you get, that's how you work these things out. As P condition Q, and this one is the topology, then this P condition Q is equivalent to the negation P or Q. So you just is a kind of proof you are doing, so that you can get the answer. The equivalence formulas. So this is all about the important law. Said this, and this is associative law, and this commutative laws, and this distributive law. You can check how these laws are. And this distributive law, identity law. So this is every law. It does this like now. If this is if you can check on this identity law, it says that P or F is equivalent to P. This one say P and the Q and the F is equivalent to F. So the component law, you can check also this law. Absorption law, it states this way. Because this one is also what you are going to use as we move. That's De Morgan's law. The De Morgan's law, that means that the eigen P or Q is equivalent to eigen P and eigen Q. And we have said that the eigen, this is it runs on the inverse, and this is the inverse. So of the previous P if we have N. So that's how you move. And let us now look on that replacement process. Consider formula A, P condition Q to condition R. The formula Q condition R is a part of the formula A. If we replace Q condition R by an equivalent formula, then the negation of Q or R in A, we get another formula of P, whereby we will be having now P condition into negation Q or R. So one can easily verify that the formulas A and P are equivalent to each other. And the process of obtaining P from A is the replacement process. Let us look on the example. Prove that P condition into Q condition R is equivalent to P, which is a pi condition to negation Q or R, which is equivalent to P, Q, which is a condition to R. So P condition into Q condition R is equivalent to P condition negation Q or R. So in this case, therefore, Q condition R is equivalent Q condition R, Q condition R is equivalent to negation Q or R. So Q condition R, this what is here, is equivalent to this one. That's what we are getting here. Are we there? Huh?
Yeah.
Yes. So that means the negation of P, the negation of B, or the negation of Q or R. Therefore, we have P condition Q, P condition Q. That means this negation and this negation are smooth. we have this one. B condition here. Because this once multiplied by this one, this negation disappears. That's one we have here. And then it's equivalent to negation P or Q. So the negation P or negation Q or R, this is an associative law. The negation P and the Q or R is a De Morgan's law, is in a De Morgan's law. And B and the Q condition R, therefore, P condition Q is equivalent to negation P or Q. Have you seen? Huh? Hello?
Sure.
Yes.
Are we together?
Yes.
Yes.
Okay.
Point.
Then example. Prove that P condition Q and R condition Q is equivalent to P or Q condition Q. P or R, sorry, condition Q. So the resolution is what you can see here. We have P condition Q or R condition Q is equivalent to negation P or Q and negation R or Q. So this one, it brings the condition the negation P and negation R or Q is equivalent to, so this and this one that's moved to this one and that one. This is a negation P and negation B and the negation R or Q is equivalent to negation P or R or Q, which is equivalent to P or R condition Q. So proof that P condition into Q condition P is equivalent to negation P into condition P condition Q. Condition Q. There is a bracket here. Then solution P condition into Q condition P is equivalent to negation P or into Q condition P. Then we have negation or negation Q or P. Then we break down here negation P or P or Q. So you open the brackets here. This moves this one and this comes here. So the T, which is replaced, negation T or negation Q. Then you have negation T. and negation P, condition Q is equivalent to negation into negation P or P condition Q. Then we have this P B all into brackets negation P or Q is equivalent to B or negation P or Q, which is equivalent to P or Q. So this P or Q returns, you can have T, which is equivalent to we have found here. So P condition Q condition P is equivalent to negation P condition into P condition Q. When you can check that example, that's another example. Now let us move to the, okay, maybe we can check the example. This is by De Morgan's law. Example shows B or Q and negation into negation P and into negation Q or negation R or negation P and hello. Hello.
Hello. Hello.
Mike, I
Hello.
can hear you.
Hello.
Are we together?
Yes.
Okay.
Yeah.
Let us now proceed. I can hear some of you are imitating me. So we were here before the networks disappeared, isn't it? We started playing music. Are we together? We were here, isn't it? Can somebody confirm? Are we together?
Yes.
Yes. We were just talking on this. This example is derived from by De Morgan's law. So I was thinking that you can just take a snap and then you just look on how it moves so that you can go through. For example, okay, let us now we add this B or Q and negation into negation P and into negation Q or negation R, then and open the brackets negation P and negation Q or negation P and negation R is a tautology. So this you need to show that this one is a tautology. So you use the De Morgan's law. And what does the De Morgan's law states? We have this one, negation P and negation Q is equivalent to negation into brackets P or Q. And then we have another one, negation P or negation R is equivalent to negation into brackets P and R. So this is a policy we are using. Therefore, negation P, are you listening?
Yes, clearly.
Yes.
Negation P and negation Q or negation P and negation R is equivalent to negation into brackets P or R. Or negation P and R. So negation into P and B or Q and P or R, they can be also negation into negation P and the negation Q or negation R, which is equivalent to negation P and negation into Q and R, which can be solved like this. Negation the P or Q and R, which is P or Q and P or R. Hence, we now have this B, we have P or Q, negation into negation P and into negation Q or negation R, which is satisfied to P or Q and B or Q and B or R, which is satisfying these examples that we are just looking on. So in this case, if you counter check, it does now driven to come to the truth. Thus, this one, all this one satisfy, we have now proved, we have shown that it is the same. So the given formula up there is a tautology. So example, show that B and the Q is a conditional to B or Q is a tautology. So solution, P and Q is a condition of P or Q, which is equivalent to negation P and the Q or B or Q. Therefore, P condition Q is equivalent to negation P or Q. And as this negation Q, negation P or negation Q or P or Q. This is by Morgan's theory or law, and this negation P as P. Somebody's talking. Who is that? Doreen. Doreen, you are supposed to mute. You need to check on your gadget. You don't need to disturb the class. You need to be conscious when you are in class. So this one is we have said that this is a De Morgan's law. This is by De Morgan's law. This one. Then B, this negation P and P or P or negation Q or Q. This is by associated law and the commutative laws. And there we have tautology, the tautology T or T by negation law. And this is as at T. That's hence the results. That's what we have. Example, we write the negation of the following statement. Jan will take a job in industry or go to graduate school. The graduate school. James will bicycle run tomorrow. If the processor is fast, then the printer is slow. Solution, let P deck the Jan will take a job in industry, and the Q, Jan will go to graduate school. This gives a statement that can be written in symbolic of P or Q. Then the negation of P or Q is given to this. Because you can combine them, then you put from outside a negation. Or else, this P or Q, the negation of P or Q is a condition of this one. Because you can even spread this, what is inside here can be the same as here. Because this negation P and the negation Q. So this what is written here and what is written here is all the same, can satisfy this. So negation P and negation Q, Jan will not take a job in industry and he will not go to graduate school. So that means, what does that mean? This, we are talking of the inverse, isn't it? Huh?
Yeah.
Yes. We are talking on the inverse. Then number P, let P, James will bicycle. This we are number P, will bicycle or run tomorrow. James will take the bicycle. That's a denote P, and the Q, James will run tomorrow. The given statement can be written on the symbolic as B or Q. The negation of P or Q is given as the negation of P or Q, and it can be all the same. What is here and this here. This is equivalent to this. So you have seen how it can be equated or equitable. So the negation of P and the negation of Q, James will not bicycle and he will not run tomorrow. So this E in a kata. So this is that means it is talking on the inverse. Let P, the processor is fast. That's number C. We add what? C, we add, if a processor is fast, then the printer is slow. So number C, let P, the processor is fast, and Q, the printer is slow. The given statement can be written in the symbolic as B or B condition Q. The negation of P condition Q is given by the negation into P condition Q. So in this case, the negation can be outside, which is P condition Q, and it can be condition the negation into negation P condition negation Q or P or Q, which can be equivalent to P and negation P, negation Q, and P, there is a bracket, B and negation Q. So the processor is fast and the printer is fast. That statement it says so. So you can look for more examples like now, part one, those statements, then you transfer them to the truth table, and that's what all we have done all through. Duality law. two formulas, A and A star, are said to duals of each other if either one can be obtained from the other by replacing this sign and by or and by this and by or. So this one can be replaced by this and this can be replaced by this. The connectivity all and are called the duals of each other. If the formula A contains this special variable true or false, then A is that A, it is duals, it's obtained by replacing true by false. For example, write the dual of the following formulas. So, number one, B all Q and R. So, B all Q and R. So, and this P and Q or R. Number three is P and Q or B or negation Q and the negation S. So the solution, the Dal formulas may be written as this. So the number one, P and Q. So this signs has changed because we have heard that it is going to be replaced by this one. So this one changed to be and this one stands to be or. So this one, this has come here and this has come here. You have seen?
Yes.
Okay.
Yes.
The same things applies to all of this. If you can check, the result one, the negation of the formula is equivalent to it is dual in which every variable is replaced by its negation. We can prove the negation of A into P1, P2, up to Pn is equivalent to the A into negation of P. Now the inverse of this, negation of E, negation of P, P1, P2, negation of P2, up to negation of Pn. So, example, prove that negation of P and Q is equivalent to negation of P or negation of P or Q, which is equivalent. This is a condition, and this is equivalent to negation of P or Q or Q. This is but A, the ends here. So solution, let us now check and then so that you can check on solving but P. So solution, we have P, negation P, B and the Q, condition negation P or negation P or Q, which is equivalent to B, P and Q or negation P or negation P or Q. Therefore, P condition Q is equivalent to negation P or Q. So P condition P and Q or negation P or Q. P and Q or negation P or Q. P and Q or negation P or Q. B or negation Q. Now you can see this has come here. B or negation Q and Q or negation P and then this has come here, or Q. Then the ideology T, P, and Q, or negation P, or Q. Now Q, or negation P, or Q. Now Q, or negation P. Negation P, or Q. So that's it. You can try part P. Then from A, you can just check and write the duals of this. The dodological imbrication. Are we to get up to that point? Hello?
Yes.
Yes.
Okay.
Yes.
Dodological imbrication. A statement formula A is said to dodological imply a statement P if and only if A the condition to P is a tautology. In this case, we write A into P, which is read as A implies P. So this whenever you see this one, it says that A implies P. They can note that this sign is not a connective. A to this one is not a statement formula. A to P is a state that A condition P is the tautology. Clearly, A implies P guarantees that P has a true value of truth whenever A has the true value of truth. So it gives us a guarantee. Can I repeat this statement? Clearly, A implies to P, it guarantees that P has a truth value of T whenever A has the truth value of T. T implies the truth. One can determine whether A implies P by constructing the truth table of A and P in the same manner as was done in the determinant of A equating to P. The example proof that B condition Q is it implies to the negation Q condition negation P. So you can just prove. You can prove that, and this is using the table. When you are asked to prove, sometimes for you to be clear with whatever that you are doing, it's good to use a true table. So let us have P, Q, and this is a negative of this. And that's why we call it negation Q and negation P and negation Q. And this P condition Q, and this negation Q condition negation P, and then this B condition Q, which is a condition to negation Q, and the condition to negation Q. So this is B. If the B it is true and this is false, this is true, then the negative of it is the false, and this is false. That's the negative of this and this. So under this one, P condition Q, and then from the previous, we had learned that this is working with the condition, and that means this will be true. Then the negative of this, the negation of Q, and the negation condition, the negation of T. So we just check on this, what is here, and then what is here. So this, because they are the same, we just give it true. And then now we are checking B condition Q, which is this one, B condition Q, this. Are we together? Are you listening? Somebody is talking. That means maybe my net has failed. Do you hear me?
Yes, we can hear you clearly.
Okay. I was saying we were here. B condition Q, the brackets, and then Q, condition to negation Q, the condition the negation P. So we are in the same thing. We are just checking on this and this. So if this is true and this is true, then it is gives true automatic. And then if this false and this false, it gives this one. This is the exercise that we have shown or we have seen previously. So it is needs to do not to trigger you. So the other connectivity, we introduce the connectivity NAND, null, which have a useful implication in the design of computers. NAND, the word NAND is a combination of not and, where not stands for negative or negation, and for the conjunction. It denotes by the symbol, this one. So you have seen, this is the symbol for the NAND. That means not and. So P NAND Q, B NAND Q is equivalent to this. The negation of the B and Q. The connectivity NAND has the following equivalence. So P NAND Q, P NAND P is equivalent to negation of P and P, which is equivalent to the negation of P as or negation of P, which is equivalent to negation of P. Have you seen? Hello?
Yes, yes.
Yeah. So, B NAND Q into brackets, and then NAND P NAND Q is equivalent to negation P NAND Q, which is equivalent to negation P and Q, which is equivalent to the negation of P and Q. Yes. P NAND P NAND Q is equivalent to negation of P NAND negation of Q, which is equivalent to negation P and negation Q, which is equivalent to P or Q. So the NAND condition is a commutative. NAND is a commutative. Let P and Q be N2 statement formulas. So P NAND Q is equivalent to negation P and Q, which is equivalent to negation of P, Q, and P. So in that change, this one does change the meaning, which is equivalent to Q NAND P. So therefore, the NAND is commutative. NAND is not associative. It's not an associative. It's a commutative. Let P, Q, and R are N3 statement formulas. Consider NAND Q NAND R is equivalent to negation P and Q NAND R, which is equivalent to negation P and negation of into brackets Q and on and R, which is equivalent to negation of P or Q and R. So P NAND Q, P NAND Q into brackets NAND R is equivalent to negation of P and Q NAND R. So negation into negation P and Q and R is equivalent to B and Q or negation R. So therefore, the connectivity NAND is not associated or is not associative. Now let us move to NOR, since we have finished to NAND. NOR. The word NOR is a combination of not and or, where not stands for negation and or for the disjunction. It denotes by the symbol this arrow. So the arrow which is pointed upwards is NAND, and the ones which is downwards is NOR. So if P and the Q are the two formulas, then P NOR Q is equivalent to the negation of P or Q. So the connectivity on NOR has the following equivalents. So P NOR Q is equivalent to negation P or P. This P NOR P, not Q, is equivalent to negation of P or P, which is equivalent to negation of P and the negation of P, which is equivalent to negation of P. Yeah. So the P NOR Q, NOR into brackets P NOR Q, is equivalent to negation of P NOR Q, which is equivalent to negation of negation P or Q, which is equivalent to B or Q. So B NOR P NOR Q NOR Q is equivalent to negation of P NOR Q NOR negation Q, which is equivalent negation P or negation Q, which is equivalent to P and Q. So NOR is commutative. Let P and Q be N2 statement formulas. So B NOR Q is equivalent to negation P or Q. So the negation of Q or P is equivalent to P NOR Q or Q NOR P. So NOR is commutative. So, and we have seen it is not associative. Let P, Q, and R be N3 statement formula. Consider B NOR Q NOR R, which is equivalent to the negation of P or Q NOR R, which is equivalent to negation of P or negation of Q or R, which is equivalent to negation of P or negation of this negation of B and the negation and the P and the Q or R, and this one is B NOR Q NOR R is equivalent to negation of P or Q NOR R. So negation and negation P or Q or R is equivalent to P or Q and negation R. Therefore, the connectivity NOR is not associated. So we can check on the evidence. Evidence 3, P NAND Q and P NOR Q are redules of each other, since the negation of P and Q is equivalent to negation of P or negation of Q. Negation into P or Q is equivalent to negation of P and negation of Q. Are we together?
Yeah.
Okay. So this is now the truth table. You can check. Example, show that A get to this B or A nor P is equivalent to A NAND P. Solution, we prove this by constructing a truth table. So this is A and B, which is being given a true. So this A in this columns P is false. Because now it is not say that it's supposed to be this and this are not to be true. But A nor P is also false. A P or A nor P can check, and this A NAND P. So you can check on this one. I'll share so that you can go through those notes, and then you change, you check, and know how it moves. Yes. Somebody is talking. Somebody is talking. So we have normal forms. We have normal forms. If a given statement formula A into P1, P2 up to Pn involves n atomic variables, we have two less by n possible combinations of true values of statement replacing the variable. So the formula of A is a tautology if A has the truth value of truth for all possible assignment of the true values, the variables B1, P2 up to Pn. So when we are talking about P1, it can be to P1, P2, P3, P4, P5 up to P100. But now n is a definite number. It's an infinity. And A is called a contradiction if A has the truth value of F for the possible assignments of the truth values of n variables. A is said to be satisfiable or is satisfiable if A has the true value of the truth for at least one combination of truth value assigned to P1, P2 up to Pn. So this you will read this, then you read on this disjunction normal function, then we have conjunctive a normal form. These ones, then you inject on the principle, the methods, all that. Yeah. Then we have the theories of inference for statement calculus. The main aim of logic is to provide rules of inference to infer a conclusion from certain premises. The theory associated with the rules of inference is known as the inference theory. So I think next time we will start from This we will start from where we have stopped. Let us start from this normal level. We will start from here, the theories of inference for statement calculus. Okay. Are we together?
Yes.
Can we get the notes?
Yeah.
Yes, I will give you the notes
Mm-hmm.
so that you go through them. So when we meet class, we will be seeing. So I can see we had only 35 students. Even there is one variation, there is one student who is on and off. So class rep. Where is the class rep?
Yes.
Yeah, make sure you have the signing list. They have signed. They sign physically. On those, I'm expecting these people who have joined the class to be the one to be signing. So, any question before we break? If there is any question, somebody may raise it that we tackle. Any question? Yes, Brian. I can see in the chat, Timothy said, I am not seeing anything. So, Timothy, you need to breathe yourself, you work on. Then you learn from others.
Excuse me,
We
sir.
understood. Yes, debate.
It was a question on negation.
Yes.
In mathematics, negation and negation is a positive state. Why not the same in proof?
Pardon?
In mathematics, negation and negation is a positive state. The consequence is a positive state. Why not the same for logic?
Why not for the same for logic?
Yeah, why not for the same in this subtopic logic?
In mathematics, the negation and negation means positive. Why not here? You see,
Yeah.
you see, we are looking on this, the way we are driving this. It gives, like, now we have come with, we talked of conjunction and all that. It negation, it means not, isn't it? According to our topic today, isn't it?
Yeah.
And the not means